Okay, I'd like to shift gears now back to binary classification because I want to talk about one of the limitations of logistic regression in that setting. And this will be a springboard for talking about neural nets. So let me make a data set. I'll call it stripes data. And what I'm going to do is make a data set of a bunch of images that are stripes. And I'll say maybe, how many stripes do I have? And then maybe the resolution of the stripes. So I'll say self.end stripes. And actually, this end stripes I'll use to refer to the number of stripes that I have. And then maybe I'll say num examples. Okay, so I'll just remember that stuff. Self.res, self.num examples. So what I'm going to say here is, okay, I'm going to generate a whole bunch of random stripe images. I'll show you what I mean in a moment. I'm going to have this many of them. Return self.num examples. And actually, I'm going to have a getItem method. But I'm going to actually kind of ignore the index. I'm going to generate just a random image. So what I'll do is I'll say pix is equal to mp.linSpace01 self.res, ji is equal to mp.meshGrid pix. So what I'm going to do is set up a grid, and I'll define an image on there. So I will say my image x is equal to np.cosine of, I'll say 2 pi times, I'll do I over the number of, no, let's see, what do we want? I want 2 times pi times the number of stripes times I. Okay, before I go any further, this is a little bit abstract until I show you a picture. So here if I were to say stripes equals stripes data, let's say maybe I'll have maybe 6 stripes. The resolution will be, maybe I'll do the same thing I did with the digits 28 by 28. Let's say 1,000 examples. Why not? So now let me say x equals stripes at index 0. I said n strips instead of n stripes. Okay, that worked. So let me just show you what this looks like. So there's my striping data. I just think I want to do higher resolution than this. Let me go all the way up to 50. And maybe I'll use slightly fewer stripes. Maybe I'll use 4 stripes just to get a little bit smoother of a transition here. Okay, so that's an image of stripes. But I want to turn this into a binary classification problem. Also, this is always the same image. Okay, so first of all, let me generate a little bit of randomness here. I'm going to add on a random phase, let's say. So I'll say this will be 2 pi times the quantity of that plus just a random number between 0 and 1. So now each time you notice the stripes move around a little bit. Okay, so that you see it's about towards the middle there. Now it's a little bit further up, that one there. So it kind of shifts around each time randomly. So I would like to randomly shift it like that. All right, the other thing I'm going to do is I'm going to randomly decide to sharpen it. So here's where the binary class comes on. I'll say if mp.random.rand is greater than 0.5, then I'll make y be 1. And in that case, I'll say x is equal to mp.sinex. So now I'll return both x and y here. And so let me make the title here be what y is. Okay. So here y is 0. It's just like it was before. When y is 1, I'm going to make these hard stripes. So there's a cutoff. You're either in the stripe or you're not. There's nothing in between. Whereas when y is 0, it's a more gradual transition. So that's my data set. So I randomly shift the thing around, and it's either a gradual stripe or a very sharp stripe. And that's my binary classification problem. So let me just take a moment to clean this up a little bit to actually return 32-bit torch tensors, and then we'll continue on with this. Okay, so I just went ahead and I returned the torch tensors as 32-bit tensors. And I was sure to flatten my image as well. Okay, so now what I want to do is the same thing I did last time. I'm going to set up a linear layer. And actually, let me store the resolution as a variable here so I can use it instead of a magic number. So I'll use the resolution of 50. And I will say, okay, I want this layer to take in a 50 by 50 image, so 50 times 50 pixels. And this time, I'm actually just going to output a single number. Remember, logistic regression, we go through the logistic function, and we output a single number, and then that number we feed to the logistic function. So in this case, we're actually just, it's going to be really just a row matrix of 2,500 numbers, and then outputting to a single number there. Okay, cool. And so then, same thing as last time. I'm going to fast forward through this a little bit, but I'm going to set up my optimizer, and I'm going to set up my training loop. So let me just go ahead and do that. All right, so I did the whole thing here that I did before. I set up my optimizer. Actually, I decided to rename my linear layer to Perceptron because that's what I called it before with logistic regression. But it turns out we can reuse this loss function, BC with logits loss. That'll just be the logistic loss when it's a single number. Yeah, so anyway, I'm gonna go for 50 epochs. I'm gonna keep track of my losses, my accuracy. Each time I'm gonna do mini batch gradient descent, so I'll take batch sizes of 50. I'll go through these examples here, and then I'll keep track of the loss and the total number that I get correct each time. So let's see what we get when I run this. So here it's going. And there's the loss, and seems like I keep hovering around 50% accuracy, which is about as bad as I could do. That's terrible. That's random guessing. I only have two classes here. Is it a smooth stripe or a sharp stripe? And it just can't make up its mind. It says, well, flip a coin. Now, is that because my learning rate's too high? I see myself oscillating a lot here, so let me turn down the learning rate a little bit. But still, I get this pattern. I just can't make up my mind. I'm oscillating around 50%. I'm just not improving at all. And so there's a fundamental mismatch here between the architecture that I've chosen of logistic regression and the data set that I have. So even though this data seems incredibly simple, there's something about it that makes it so that it is not linearly separable, because that's what I've assumed for logistic regression, right? That I can actually linearly separate my data. So let me dig in and see why that might be. What I'm going to do actually one thing I'll do just to kind of validate that I'm not really learning much of anything. Let me just look at the weights here. So I'll say W is equal to next iter perceptron.parameters. And actually, let's see, I should have a bias too. So I guess I'll say WB, let me just check that. Oh wait, I just have the weights now. I don't have a bias anymore. Okay, but anyway, so I look at this and I say, if I say w.view res. So let me do that. No. Oh, right, again. So these are differential parameters, so I have to say detach first, to take them out of gradient mode, and then I can look. But anyway, so it's taking the dot product of each image with this, and this is just noise. It really learned nothing. So why is that happening? Well, maybe what I'll do is I'll take out a bunch of random examples now. And actually, there's another thing I want to remember here. So let me also return this. I'll call this random number P for phase. This is going to indicate the shift that the stripe has gone through, because that's going to help me in a moment. So let me actually return all that stuff here. I'll ignore this, in the learning here, but I will remember this when I go to look at the data. So, and let's actually take slightly larger amount of data here. So let me go ahead and what I'll do here is I'll take out all the data basically. I'll say loader is equal to data loader, data set, I'll say batch size equals length of data set. Or no, what I call it here, I call it stripes. Okay. So let me take out all the data. Let's just check about that. So I'll say x, y, p is equal to next iter loader. I'll just print x.shape here. Okay, so I've got all my data, 5,000 images, which are 50 by 50. Let me take these out into NumPy actually, because I'm about to do some plotting stuff. y.numpy, p is equal to p.numpy. And actually, I'm going to turn back to my old friend, PCA. Remember PCA? This is an unsupervised dimension reduction technique that we talked about, which tries to find the directions of most variance in our data set. So let me look for the top 2 directions of most variance in my data set. So I say from sklearn. So I'm not going to, I showed in class how to implement PCA from scratch by doing an eigen decomposition of this matrix. But I'm just going to use, there's another library called scikit-learn, sklearn, that's already implemented PCA for me. So I'll say PCA is equal to PCA n, let's see, n components, I think it is, equals 2. And so I'm going to find the directions in my 2500 dimensional data space of highest variance. And what I'll say is, I'll say here, I'll say maybe x dr for dimension reduced is equal to pca.fit transform x. Okay, so what I'm going to do now is project data onto 2 dimensions of highest variance. Okay, so let's say from sklearn. Oh, I meant to say import PCA. There we go. All right, so PCA ran, and I look at this, and now I actually only have 2 dimensions. So let me go ahead and plot these. So I'll say plt.scatter. Let me plot the projection onto the axis of highest variance on the x-axis. I'll project, or I'll plot the projection onto the axis of second most variance that's perpendicular to that on the y-axis. And here's what I get. Okay, that's kind of interesting. Let me color that actually by the class that it's part of. So I'll say c is equal to y here. Okay, so what I notice is, so blue is 0 here, and yellow is 1. So 0, remember, is the smooth stripe, and 1 is the harsh, the stripe transition that is very, just black and white and nothing in between. So what we see is the ones that are black and white and nothing in between are on a ring out here, and the ones that are smooth are in a ring inside of it. And it looks like this is not linearly separable just looking at it. What we have to remember though is this is in high dimension. So how do we know that this circle is not above the other one? Actually, it turns out for this inner circle, I only need 2 dimensions to represent it. So when I do the projection, I'm fully preserving the geometry of this inner circle. The outer circle needs more dimensions to represent it, but when I project it onto the plane of the inner one, so for the smooth ones, I can't separate it. So actually it turns out this fully describes the inner ring here, and that means that, yeah, when I project the outer ring onto the plane of the inner ring, so the outer ring is a little bit curvier. It still makes a loop, but it's just a curvier loop. When I project the outer ring onto the plane of the inner ring, I end up with this situation, and you just cannot linearly separate it. You cannot choose a plane that cuts the yellow from the blue here. And so actually I'm going to take a moment, I'll create a little animation to show you why these are rings. But the conclusion here is this data is not linearly separable, so I shouldn't expect logistic regression to do very well. And because I've sampled evenly from each class, the best that I should expect to be able to do is to cut through the middle, or to put all the data on one side or all the data on the other side. So I could sort of like cut it in half and say, okay, half of the smooth stripes are smooth and half of the harsh stripes are smooth, and then vice versa. Or I could just say everything's smooth, and either way I'm going to get only 50% accuracy. Okay, but let me just take a moment to make a little animation that I think will explain a little more why the geometry is actually like this. Okay, so I wrote a little bit of code to make an animation here. What I've done is I've actually sorted each of these points by their phase, by that little amount that I was adding in on the inside of the stripe. And so if I look at that, now I'm gonna show you these points. Now they're sorted by phase, and so here's the image, and here's where it actually projected to on this plane. And so here I'm showing you all the smooth ones. So as I promised, the smooth ones ended up on the inside. And again, actually, I only need the 2 dimensions that PCA learned are the only 2 dimensions that I need to fully represent the geometry. Even though these have 2,500 pixels, I only actually need 2 dimensions to represent those. If I look at the ring on the outside, well, that is all of these harsh squares here. Turns out 2 dimensions is not quite enough to represent that outside square. But anyway, you see, yeah, so the shift is taking me around the circle, and eventually I'll end up back where I started. And actually, yeah, maybe this is really all I want you to know, is that, hey, I can make some data set. It's not linearly separable. I tried to train it. I couldn't. And actually, I can see from PCA that it's not. It appears not to be. To finish the proof, for those interested, I will actually try to convince you why this is the case mathematically. But I'm happy if you stop here and just accept the fact that we have a data set that's not linearly separable. And next, I'm going to show you how to address that and actually train neural networks, which will be able to separate things like this. Okay. Okay, but for those who are interested, let's get a little bit more deeply into the math here, because it's kind of a cool example. So if I look at the equation that I used for the stripe, it was this. So let me just copy it down here so I have it. So just translating that into ordinary math notation, I'd say, okay, that's the cosine of 2 pi, and maybe I'll just say n for the number of stripes, and I'll say plus phi. Okay, so if I distribute through this p here with the 2 pi, this whole thing can simplify into cosine of 2 pi n plus phi, where phi is the thing that varies, but n is fixed. All right. So what I can do is apply a trig identity here, and I can write this as cosine of 2 pi n cosine of phi plus sine of 2 pi n times sine of phi. So that's a trig identity that I can use to split this up. And now what I see, okay, as I vary phi, this is a constant times cosine plus a constant times sine. And so actually what's happening in higher dimensions is this term here is actually, it turns out to be an image. So if I look at that, if I was going to say pix is equal to np dot length space 0, 1, and what did I say here? 4 stripes? Yeah, 4. So ji is equal to np dot mesh grid pix. So if I were to say p2.im show cosine of 2 pi times, oh yeah, let me do it this way, times np.pi, so 2 pi times 4 times pix. Oh geez, what did I do? Float cannot be interpreted as an integer. I meant to say between, oh yeah, sorry, I meant to say here, what is this, a 50 dimensional image, 50 by 50. I screwed something else up here. What did I screw up? 2 pi times 4 times I meant to say. Okay. Okay, anyway, so this here is one image. And then I have another image, which is the sine of it. So let me look at that. Okay, so here's the cosine here, and here's the sine. And it turns out I can represent any striped image with the smooth stripes as a linear combination of the first image and the second image, where the weights are determined by cosine of phi and sine of phi. So just to show you what I mean, if let's say, maybe I'll make phi pi over 3 or something. So if I look at that, maybe I'll call the first image capital C and the second image capital S for sine. And here I were to say plt.im show, I'll say it's supposed to be cosine of phi times C plus sine of phi times S. And so this is a different image. It's not quite this one or that one. I can move this along anywhere I want. So maybe I'll go mt.pi, that'll move it down a little bit further. Maybe I'll go even further. Maybe I'll say pi times 1.5. That moved it down even further. So my point is, from these two images, you can get any smooth striped image as a linear combination of these two. And so that's why I'm telling you, that's why I insisted that actually PCA learned the flat here, the 2 dimensions. So for these stripes. As I vary phi, I'm stuck in a plane. The first coordinate of the plane is actually, it's in high dimensions, it's a little bit weird, but in 2500 dimensional space, it's this image. The second coordinate is this image. All right? But for this one, I actually have something a little more complicated. So I can actually write an expression for this one, but it's a little more complicated. So it starts off like this, but I compose it with a sign function, or a function that makes this positive 1 when it's greater than 0, or negative 1 when it's less than 0. And so that's actually something called a square wave. And so there is a formula for this using something called Fourier series. And the formula is actually, we would say here that our image is going to be equal to 4 over pi times the quantity of, okay, we're going to start with sine of 2 pi. So we'll have sine of 2 pi n and then we're going to have plus 1/3 sine of 6 pi n plus 1/5 of sine of, let's see, no, I didn't get that right. So it was, no, 2 pi n, yes, 1/3 of 6 pi n, yes. So 2 pi times 3 times n times 1/5 of 2 pi times 5 times n, which is 10 pi n. And you just keep going like this. 1/7 times sine of 14 pi n. And this goes on forever, actually. So actually, just to kind of convince you, I'll show you in one dimension. Or no, I can do it here. I can do this in a loop. So maybe I'll say, all right, my image I is equal to zeros, res, and I'll say for I in range. Maybe I'll do the first 5. They're called harmonics here. I'll say, all right, my actual index here is going to be 2 times I plus 1. So I'll say I plus equals 4 over pi times sine of 2 pi times the number of stripes I had times k over k. I think that'll do it. So let's see what that looks like. Okay, that didn't quite work. Let's see what I missed here. I meant to say times sine of 2 pi times 4 times k times I. Okay, hang on. Let me pause for a second to figure out what it. Oh, no. I overrode my I here. I know what I did. Okay, so starting over here, I should say not I is equal to np.0s, or maybe image is equal to np.0s. Okay, there we go. So anyway, all right, if I start out, let's say I just loop through the first two harmonics, I see it's still pretty smooth here. But the more that I go through, let's say I go through 20, the closer it gets to being a very sharp stripe. Okay. Now the same kind of thing is going to happen if I do a phase shift here. If I put if I take this equation and I put the phi on the inside of this, so here I said, this here was saying that my image of I got myself all mixed up here because I meant to say 2 pi n times y, where y was the y coordinate of this. Okay, 10 pi n times y, 14 pi n times y. So my function f of y here is equal to this whole thing, which is called a Fourier series of the square wave, as a function of y. I could then say, let me compose this with a phase shift, just like I did for the other one. Let me allow you to shift this down. And so maybe I'll say, okay, I'm going to do y plus phi here. I'll shift this, I'll allow you to shift this. And so if I plug that in to each of these in the place of y, I'll end up again with something like I did before with the cosine. So 2 pi n times the quantity y plus phi. And then I'm going to do another thing where this time this sine addition identity, where I can split this up into a cosine and a sine times things. And so anyway, the upshot is, I'm going to stop with the math here, but the upshot is you end up with 2 dimensions for each of these. The first 2 dimensions are going to coincide with the 2 dimensions of the smooth one, because the smooth one was just 2 pi times n times y. Yes, I meant to write that up here. 2 times pi times n times y. So the first one was just cosine of 2 pi times n times y plus sine of 2 pi times n times y. So the square wave, the sharp one, has those first 2 in common, the cosine and the sine of them. But then it's going to have other ones, and each of those is going to contribute an extra pair of dimensions. And it turns out we need actually all of the dimensions to perfectly represent. You can see I'm not quite there. I'm getting there. If I go up, let's say I go up to 50 here. Now I'm a lot closer, but I'm still not quite perfect. So I have to actually use all the dimensions that I have at my disposal. In this case, it'll be 2500 over 2. Well, I didn't like that. Oh, I guess I should have said divided by 2. Okay, so this actually will get me all the way there if I use all the dimensions. This is just 0 here, so it turns out, yeah, that's just a little artifact there. But you have to use all my dimensions. But they do coincide on the first 2, the cosine of 2 pi n y and the sine of 2 pi n y, those images here. And the reason that you see that the smooth one is the ring on the inside in those 2 dimensions is because the square wave actually has the factor 4 over pi on the outside, which is greater than 1. So the radius in that plane here of the square ones is actually greater than the radius of these, and that's what makes this gap here and makes them not linearly separable. Okay, so hopefully that math was interesting to some people. Now we'll move on to addressing the problem and actually looking at neural nets.